as you can see today, we are going to move on from chapter 1. All right, chapter 1 was an overview of the entire biology year, things that you should keep in mind throughout as we are going through these chapters and we're going through these concepts. I'm going to bring up the idea of emergent properties. I'm going to bring up the concept of evolution and how what we're talking about is related to evolution. I'm going to bring up structure and function relationships as we go through. All right? So this is all related. And I know, yes, that these slides are not up, and that's okay. They will be up today, this afternoon. All right? And more importantly, I want you to pay attention. Okay? And also, this recording lecture will also be posted as well, so you can go through. So, with the idea of structure and function, emergent properties, interactions, how things interact, we are going to move on to the next step. All right? Before we move on, and we start chemistry, let's go through the idea. What did we say? How we talked about biological life is life, fun, really, Max? Come on. It's diverse. Okay, so we'll say the idea of biology, this is going to be kind of scratchy writing, but we'll do it, right? We said that it was diverse. What else? Unified. There's a unity to it, right? And what else did we talk about? Structure, function. We said life was structured, it was organized, right? What are those levels of organization? Do you remember? Ooh. Do you remember some of them? All right, so we're going to go from top to bottom. So we're going to start with your biosphere, to ecosystems, to communities, to keep going. Okay. What else? Well, we'll do organs and organ systems, tissues, cells, organelles, molecules, right, and atoms. Okay? Those are your levels of biological organization, from up here being the most inclusive. What does that mean? What does biosphere meaning most inclusive? Includes everything. Includes most things, right? Well, the biosphere kind of includes everything, right? So it is the most inclusive, and the least inclusive would be atoms. Okay? How often do you experience an atom by itself freely available? Not very often. It's very, very seldom that you actually experience an atom of oxygen. Usually you have oxygen in the form of what? Air. What is it though? It's a gas. Max. There's 2 oxygens, so usually it's O2, oxygen gas. All right? So we're going to talk about those interactions. We're going to talk about atoms, okay? And then we're going to talk about the interactions among atoms. So we're going to talk about atoms, and then interactions that lead to molecules. And with that, today we're going to talk about the emergent properties that occur after atoms interact. Okay? Questions on that? So, we know that biology is dependent upon other things. Really, biology is an all-encompassing idea. All of life, kind of what happens in life is dictated by chemistry and physical properties, right? What happens in your body is dictated by the chemical and physical properties the atoms that you're made up of, all right? So you are bound by the basic laws of physics and chemistry, for the most part, okay? So one of the examples is the use of formic acid by ants to maintain devil's gardens, right? The stands of durian trees. So ants, in this case, use formic acid, which is an acid, right? But they produce it, and the trees utilize it, right? So no matter what you're thinking about, if you think about any process in your body that is dictated by chemical and physical properties. Give me an example. Digestion, okay? I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I'm sure there's probably all of you have water bottles in your bags. Give me an example how the ingestion of water is going to lead, or what you digest is going to lead to the function, and based upon its physical properties. Think about it. Okay, Max, or you got one big fat bottle of water over there, right? Max is going to have about 4 of those today, hopefully. What does that do to his body and his kidneys? Think about it. Talk about it with your neighbor, and come back to me. Go. Think about it. Talk about it, and come back. I don't like this setup they have going on. All right. It is. How are we? So what do we think? What'd you come up with? Anything. How is the ingestion of a large volume of water going to, because what is water in the first sense? It's a liquid. It is H2O. That means there's how many atoms make up water? 3. 2 atoms of hydrogen, 1 of oxygen. But now the idea of this is that life, right, biology is subject to the basic laws of physics and chemistry. So how does the ingestion of water affect your life processes? That's what we're thinking about. What'd you come up with? So Max is going to drink a lot of water. What's going to happen? What's going to happen to his body? Nothing? Something? Max? He's going to become hydrated. Continues to drink. What's the rest of his body going to do? It's going to filter it. There's going to be some absorption that's going to occur. What else is important for that water intake for your body? What if he has 2.5 gallons of water instead of? You're going to get rid of it, right? We're going to remove excess water. Okay? So a lot of your body processes, how you absorb nutrients, how you, your blood volume, the acid-base balance in your blood is dependent upon the amount of water that's taken in. Okay? And the chemistry of water, what we'll talk about today, right, dictates how those processes occur. Okay? Questions on that? We're gonna go through it a little bit. Don't be too crazy about it. All right? But basically, what is an atom? The smallest unit of matter. That's the book definition, right? So it is the smallest unit of matter, right? The smallest thing you can get of a substance that has the properties of that substance. Once you get smaller than that, it gets all crazy, okay? So matter is composed of chemical elements, one of which I just gave you a little while ago. Oxygen is an element, okay? So we have matter is anything that takes up space and has mass. So it has to have mass and volume. All right? Your matter is made up of elements. Give me an example. I gave you an example of element oxygen. Give me some more. Glucose is not an element. What was that? Hydrogen. What else? Helium. Lithium. Sodium. Carbon. Carbon's a big one. Okay? All of those are substances that cannot be broken down into other substances without changing their properties. All right? So you could take glucose and break glucose down into C6H12O6. Right? That's the chemical formula for glucose. C6H12O6. But we can break that into, and our bodies do it all the time, break it into water and carbon dioxide. Okay? And then we could break down water into two hydrogens and an oxygen. And we could break down carbon dioxide into two oxygens and a carbon. We cannot break down carbon into half a carbon without changing the way it behaves. Okay? Could you physically break down carbon into its atomic particles? Yes, you could. You could take the 4 electrons in the outer shell of carbon and pull them off and break them down with a lot of technical expertise and other, specialized equipment. However, carbon will no longer behave as it does naturally as carbon. Okay? A compound is a substance consisting of 2 or more elements in a fixed ratio. Up here I wrote a bunch of stuff. Which one of these is a compound? Give me an example of a compound that I've written up there. Glucose. Okay? C6H12O6. Is that a fixed ratio? Right? 1 carbon to 2 hydrogens to 1 to 2 to 1. What about H2O? Yes. 2 hydrogens, 1 oxygen. Those are compounds. So now it says it has characteristics different from those of its elements. What does that mean? So what we're going to do here is we're going to take hydrogen plus oxygen and we're going to make water. What is water at room temperature? It's a liquid. What is hydrogen and oxygen at room temperature? Gases. So there, by itself, that little interaction has changed the properties. The compound has different characteristics than its elements. What is this an example of? Emergent properties. Okay? We have an interaction of atoms. Okay? An interaction of 2 things now that have taken on different characteristics. Those are your emergent properties. Okay, here's some elements that are important in the body. Oxygen, carbon, hydrogen, nitrogen. Right, that makes up about 96% of your body. And then you have calcium, phosphorus, potassium, sulfur, sodium, chlorine, magnesium. Right, make up most of the rest. Then you have trace elements which are less than 0.01% of your body mass. Include iodine, fluorine, iron, manganese. Now, fluorine and iodine, are they important? But all right, you say yes. How many say yes? They are important, okay. But they only make up less than 0.01% of your body. Why are they so important? Where do you find fluorine? Where is it important? Where is it? How does your body get it? Mike?
When you're developing as a fetus.
Okay, developing as a fetus. I'm going to argue that you guys get it every day. You brush your teeth. You have fluoride toothpaste. In some cases, it's in your drinking water. Yes, Mike, it is imperative that you get it while developing, right? But you get it every day, okay? Where do you get iodine? Salt, iodized salt, okay? What happens when you don't get enough iodine? Anyone? Mike? Goiter. Goiter is a swelling of the thyroid gland because the thyroid, you guys who were in my anatomy class should have known this, right? Okay. You get swelling of the thyroid gland because it's trying to extract as much iodine out of the body as possible. Okay. And if it's there in low amounts, then it swells and so on. Because the thyroid hormone uses iodine, right, is to form. So iodine, these trace elements, although they are very little very small in terms of the amount of the total body mass, they still have very high importance. A lot of the times, these trace elements are important in how reactions occur in the body. Okay? Example of element. So, how do those interact? The next question is, how do those interactions between elements occur and what governs them? Right, so we talked about an element consists of unique atoms. An elemental oxygen consists of 2 oxygen atoms, right? An atom is the smallest unit of matter. And this is the important part, that still retains the properties of that element. It still acts like oxygen, right? It still acts like carbon. If it doesn't act that way, then it's no longer an atom of that substance. Okay? Atoms are composed of subatomic particles, right, including neutrons, protons, and electrons. So let's draw out the structure of an atom. So we're going to use oxygen here. Oxygen is atomic number 16. 16?
Yes.
Yeah. Carbon's 14. Yeah, 16. Topic number 16. What that means is what? It has 16 protons. Okay? Atomic number is equal to the number of protons. Okay? Protons and neutrons are found in the nucleus. So, let's draw the nucleus of oxygen here. I'm going to put, actually, I'm going to do it this way. Let's erase that. Make that a little bit bigger. Okay, we're going to put the number 16 in red and the number 16 in blue. Yes?
It has an atomic number of 8.
Who's screwing with me? All right, it's the same difference. It'll still be the number, but we'll go to 8. I forget these things. 16 is sulfur, which would end up having basically the same number, except. So, let's turn that over to atomic number 8. Okay? So now our nucleus is 8 protons and 8 neutrons. Okay? I did them in red and blue because the protons are what charged? Positive charge. Neutrons are neutral. Okay? Neutrons are neutral. No charge. Okay? Now, elemental oxygen normally, in most cases that we're going to be worried about, the number of protons is normally equal. In most cases, is equal to the number of electrons. Okay? Where are electrons in atoms? Outside of the nucleus. They orbit the nucleus in distinct shells. Okay? Have you started this in chemistry yet? No, you will. Sorry. Okay? So we have shells. We'll do these in green. Okay? So here's our shell. The first shell fills with 2 electrons orbiting the nucleus. Okay? And then from this, now we have to move up in energy level. So we move up in energy level to the next shell. And for the most part, every subsequent shell after this will fill or be satisfied, happy, when 8 electrons are orbiting in that shell. Okay? So we have 6 electrons that we have to put somewhere, right? We'll put 1, 2, 3, 4, 5, 6. So if oxygen here has 6 electrons orbiting its outer shell, is it happy? No. Is it, let's say, is it stable yet? No. It is what we call reactive. It will react with other atoms to gain a full and stable outer shell. How does it do that? It can bond to itself. It can. So what's the idea? You could either, the rule is, I want to get to this magic number of 8. 8, that's the magic number. How can an atom get to that full outer shell, that 8 number? It can share electrons. He passed kindergarten. He's a good sharer, right? What else? Can gain electrons, or it can lose electrons. Okay? So we can gain 2, lose how many? 6. Is it easier to gain 2 or lose 6? Gain 2. Okay? This is important because when we start talking about other elements, like carbon, which only has 4, carbon 4 is kind of like in the middle. It could lose 4. It could gain 4. It could share. Okay? So we're going to go through those type of bonds. Questions on the nucleus right now? All right, so we have a cloud of electrons that orbit the nucleus. When we do it, I like to show it in these Bohr models, these non-space filling models, just to see where the shells are. Okay? Questions on shells? Okay? So, here's neon. Neon has 10 electrons. Is neon reactive? Yes or no? Why not? Because why?
Its shells are filled.
Its shells are, which shell is filled? The outer shell is filled. Okay? Now, if the outer shell is filled, chances are the inner shells are filled, right? All right, so we are only really concerned with what the state of the outer electron shell is. Otherwise, I don't really care. Okay? And so this is what the orbital, we call these orbitals. What are these electron distribution diagrams showing? So we have the first shell, 1s2. That means there's 2 electrons. And then we go to the 2s orbital, and then the 3 2p orbitals. What is that? What do you think that is? How many electrons fit in the first shell? 2. So 1, if I do 1s2, that's a full shell. Now, how many electrons fit in the second shell? 8. So 2s2 and 3 2p, how many electrons do I have left over to fit in there? 6. So 2p6. Okay? Now that's a total of 10. That's two full outer shells, or 2 full shells. Okay? You're going to go through that in chemistry, go through 1s2, 2s2 orbitals. What this is in terms of biology, this is how those electrons move around the nucleus. All right? So, we used oxygen. We said oxygen has 6 electrons in its outer shell. So what? Needs how many? It would like to get to the magic number of 8. So it could gain or lose electrons, or it could share. And that's what chemical bonding is. Eventually, chemical bonding, the interactions between elements, the goal is to develop a stable outer shell. And the reactions will do so that the elements that are involved in those reactions get as close as possible to that stable outer shell. We can do this through sharing electrons or a covalent bond. Covalent, co means sharing. Valent refers to the valence shell. What is the valence shell? The outer shell. The valence equals outer. So valence equals outer. I will try to be better penmanship on this, but it's just the way it is. All right? And so we can share electrons. We could also gain or lose electrons as well. When we gain or lose electrons, though, that is called an ionic bond. Okay? So let's do a nice ionic bond. Sodium plus chlorine yields NaCl. Okay? What is sodium's atomic number? What is chlorine's atomic number? You don't know it? Look it up. And no, you don't have to know the atomic numbers. Okay? I just don't want to have another Max saying 16. So chlorine is atomic number 17. And sodium is atomic number 11. Okay? So how many electrons are in each of these atoms' outer shells? Do the orbitals, figure it out. You can talk with your neighbor, and I will draw only the outer shell of sodium and chlorine. So, how many electrons does sodium have? How many electrons total does sodium have? 11. How many protons does sodium have? 11. Okay. How many neutrons does sodium have? Trick question, you don't know. Why don't you know? Because we don't know the atomic mass yet. We'll talk about that in a little bit. So the atomic mass will tell you what and how many neutrons are there. You could end up with an atom or an element that has more neutrons than protons or electrons. Okay? That is naturally occurring. We'll talk about that in a little bit. So that was a trick question. So we know 11 protons, 11 electrons. How many electrons in its outer shell? 1. What's the easiest route for sodium to get to a stable state? What's the magic number we want? We want 8. What is its lower shell? Its outer shell has 1. What is the next lower shell has how many? 8. Is it full? Yes. Okay. So, easier for sodium to lose 1. Let's look at chlorine. Chlorine has 17 protons. How many electrons? And how many of those are on the outer shell? 7. Easier to get to 8, how? Gain 1. And that's exactly what happens. So this little sodium guy goes, see ya. Comes over here. Hey guys, how you doing? We're cool. Yeah. What happens when that electron what goes with it? That electron goes from sodium to chlorine. What does it take with it? It's negative charge. Okay, I heard someone over here say it takes its negative charge with it. So now, here, how many electrons does it have now that it's lost this one? 10. It has 10. 10 electrons. How many protons? 11 protons. What about chlorine? How many electrons does it have now? 18 electrons. How many protons? 17 protons. Which means, what's the net charge? This is a positive 1. This is a negative 1. Right? It has a net negative charge. Let's erase that a little bit so it actually looks like a negative. Okay? So, that's the only interaction that those two have atomically. Right? At the atom level, that's how sodium and chlorine interact. But you know sodium chloride is what? Salt. Salt, if you look at it, what does it look like? Give me an example. It's a crystal structure. Okay? How does that stay together? How does sodium and chlorine stay together? This is an ionic interaction. Positive and negative charges, opposites attract, correct? So what you end up having is these two ions, a positive ion, a negative ion, cation, and anion, they attract to one another and form your crystal structure. Okay? That's an ion. Okay? So here's an example of some covalent bonds. We'll talk about those in a second. Questions on ionic bonds and what they are. We're going to go over them in a second. We'll show you the picture of chlorine or sodium in a minute. Okay? For covalent bonds. Covalent bonds are a little more involved. Okay? The reason why is there's a property of what we call electronegativity. So a covalent bond is sharing, right? Yes. So I'm going to minimize this for a little bit. And we're going to go through a covalent bond now. Okay? Covalent bonds. We're going to use oxygen as our example. Okay? Atomic number 8 has 6 electrons in its outer shell. Okay? So let's draw one atom of oxygen here. So oxygen right? We're gonna do, let's do it this way. We'll do oxygen here, and that's 6, okay, and it has 1, 2, 3, 4, 5, 6, okay? It needs to get to 8. Here's our other oxygen. Okay, 6. Okay? So now we know oxygen by itself does not, I'll do oxygen, okay? Oxygen does not really exist elementally. It always, basically, is always in the form of a covalent bond, okay? So now, in order for these two to come together, what do they have to do? They're going to share. Oxygen is kind of a bully, all right? It's going to tell other atoms, I'm not giving up electrons. Matter of fact, I'm going to take them from you. And I'm going to take them, and it's not going to be equal sharing, okay? Except, in this case, there's 2 elements of oxygen, so they can't really bully each other around, right? All right, so they have to share equally. That equal sharing of electrons is what we call a non-polar covalent bond, all right? So we're going to put these two together. We're going to have one here, and I'm going to have one here, okay? How many electrons do they need to share to get to the 8 magic number? 2. So we're going to put 2 electrons here that they're going to share, and then we'll fill in the rest. 1, 2, 3, 4, 5, 6, 7, 8, right? So this element of this oxygen atom has 8 electrons, stable, yes or no? Yes. This atom of oxygen, 8 electrons in its outer shell, stable, yes or no? Yes. Okay? The shared electrons spend equal amount of time. They have joint custody between the 2 parents. Okay? They spend equal amount of time with each original oxygen element or oxygen atom. Okay? Are we clear on that? Yes? So, what happens now when oxygen can be a bully? What happens when you have your oxygen, your 6 protons, right? Your 6 electrons. 1, 2, 3, 4, 5, 6. Okay? Now it's going to share electrons with hydrogen. How many electrons does hydrogen have in its outer shell? 1. You think hydrogen is going to give up its electron? You think hydrogen is going to give up his lunch money to the oxygen bully? No, it's the only one I got. Okay? It's the only one he has. So, are they going to share? Yes. Are they going to share equally? No. All right? So, yes, they're going to share, but we've said that the electrons travel around, they orbit the nucleus of an atom. Okay? So, when you get a large electronegative atom, such as oxygen, you get a bully, they hold on to the electron longer. Okay? So your electron here, hydrogen's electron, will travel and spend more time in the oxygen side than it will on the hydrogen side. So if this was its flight, it'd be like that. Okay? More time on the oxygen side than on the hydrogen side. Okay? This is what we call a polar covalent bond. One side holds on to the electron longer. Right? So polar. Simply saying there's an unequal sharing. Oxygen's going to hog the electron a little bit. But when oxygen hogs the electron, what does it also get? It's holding on to the electron, it gets its negative charge. All right? So we call water, this is a water molecule, a polar molecule because it has two sides. It has a negative charge side. Electrons are on that side longer, okay, versus a positive charge side. Less electrons aren't there as long as on the other side. Okay? Questions on covalent bonds. Sharing, it can be equal, it can be unequal. All right? And so you have an explanation of that here. You have your nonpolar covalent bond, they share equally. A polar covalent bond, one atom, is more electronegative. Electronegative could be described as a measurement of how bullyish the atom is, how stubborn they are, how they do not like to share. Okay? And what that does is the unequal sharing causes a partial positive or negative charge for each atom or the molecule, based upon where that electron is going to be most of the time. All right, so here's water in a space-filling molecule. You see big bully oxygen holds on to the electrons a little longer, gives a net positive charge to the hydrogens, a net negative charge to the oxygen. Okay, here's our ionic bonds of sodium and chlorine, which we already covered. All right? And there you have your cation and anion as they are. Right? So the movement of a sodium electron over fills both, fills the needs of both. You have a full shell for sodium, a full shell for chlorine, and you end up with those positive and negative charges. Now they're ions. Cation is a positively charged ion, while an anion is a negatively charged ion. And then those ions, positive and negative charges, stick together, giving you your crystal structure of salt. Okay? What we call a crystal or a lattice work, right? A lattice structure of salt. Questions on covalent, nonpolar, polar bonds, ionic bonds, structure of atoms, etc. Yes?
What was the anion versus the cation?
A cation is a positively charged ion, so it's basically lost the electron, and an anion is negatively charged, it has gained the electron. Okay?